welcome you to this session for AP Physics 1. I'm John from Marco Learning. I'm joined by Gina Ruiz-Houston from the great state of Florida, who is an expert in all matters AP Physics. Gina, I'm going to turn it over to you for our review. This will last about 1 hour. We're going to post it in our channel, and I encourage you through the chat, go ahead and press that like button and keep us posted with the questions that you've got. Gina?
Okay, great. Wonderful to have you guys here. So exciting. We're going to finish up our APs tomorrow. Yes. And I'm sure Saturday morning, you'll all be asleep, me included. So yes, we get our last exams tomorrow. Some of you might be taking the Physics 1 and 2 exam. If so, bless your heart. Our AP Physics 1 exam is bright and early. So let's, without further ado, can we go ahead and get started so we can get you guys through this? Now I'm going to first put in the chat, hold on, right there. I put a link there in the chat, which is to our very famous College Board equation sheet and constant sheet. If your teacher didn't give you your own soft or hard copy, there it is for you to look at real quick before you go to bed tonight and real quick in the morning when you wake up. When you do open your exam, you're going to have a copy there that you can tear out and use now on all sections of the exam. And you might say, Miss Ruiz, why are you making a big deal about this? Because there used to be the time when the equation sheet could only be used on a certain section of the test and a calculator could only be used on a certain section of the test. But now you're welcome to use both on all sections of the test. So count it as a blessing. All right. For our facts and our FAQs, surprise, surprise, our exam date is tomorrow, 8 a.m. sharp. Depending upon where you go to school, they may have you coming in early or extra early and feeding you breakfast, or they might have you just starting out right around 7:30 in the room so you can start processing all that paperwork of getting the labels in the right places. But you'll start pretty promptly at 8 a.m. Now, remember, your test is going to be 3 hours. Okay? That's a lot of physics straight for 3 hours. So pace yourself, okay? Make sure you have a good breakfast. Make sure you get some sleep tonight, but pace yourself because you only have one little window in between the multiple choice and the free response to really get a good stretch, get some air in your lungs, and rethink and refocus, okay? So remember, our test is 50% multiple choice and 50% free response. So with the multiple choice, yeah, we've got our 50 questions. But with the free response, no, we've got our 5 different questions. And they have different values for the different kinds of questions. So the total for free response might not exactly be 50. But that's okay, because we're going to count the test 50% multiple choice and 50% free response. So equally counted, okay? Now, multiple choice section, just to go over, because, you know, sometimes we get a little nervous before the test. We do have our 50 questions. We do have our hour and a half or 90 minutes to do this. Now, the questions could be discrete or they can be in question sets. What does that mean? That means I could just be an individual question. Some sort of prompt, maybe some sort of picture. They ask you a question, you pick A, B, C, or D, you're done. Okay. Other questions, though, they link them. So you might have a diagram or a premise, and it might be 2 or 3 questions that go with that diagram or premise. If so, that's considered a question set. Now, if you lose, say, one of those questions in the question set, that doesn't mean you're going to lose the other 2 if you get them right. Okay. So they don't like add on to each other. They're not attached other than having that stem being the thing that you're looking at. Okay. And your teacher has probably talked to you about those cute little 5 questions right there at the end. Ooh, you're so excited. Those are going to be your multiple select. Now, students always ask, well, you know, what if I put one of the correct answers, but not the second answer correct? Do I get like half of a point? No. You have to get both pieces correct to get that point, okay? So of these 50 questions, let's say number 49, you put A and B, and it was supposed to be A and C, okay? You lose that point, okay? And those double answers do not count more or less than any other question there. So think about it. Most people like to answer the single answers first and then get to the double answers, okay? Because it takes a little bit more work to do those double answers. And all 50 count exactly the same. Now, what you're trying to do is you're going to try to maximize your score on those multiple choice. As many of them as you can get through and get that correct answer, do it. Eliminate the answers that make absolutely no sense. And if you have to narrow it down to 2 and pick your best one, go for it. Let's say I'm just, my teacher never got to that section, or I was sick during that section. I never went over that. Okay. If you have absolutely no clue, pick a letter and stay with that letter. So any question that you have no clue, let's say your favorite letter is A, pick A, okay? And statistically, you'll probably get 1 or 2 of those right, okay? But you don't know them, but you're going to do your best guess on everything that you have there, okay? Our other half of the test is our beautiful free response. And I say beautiful because you can get your partial credit. With the multiple choice, you're either right or wrong. It happens. But with the free response, I can reason out my answer. I can show them what I'm thinking, and I can get partial credit on any or all of it. So that's kind of nice about the free response. It allows you to be a bit more creative and to truly express yourself with physics. Now, our free response for our test for Physics 1 is different than C, Mechanics, EM, different than 2. We have our own entity here, okay? Now, this entity is changing for next year, but you don't care. You're doing this year, okay? We get our hour and a half or 90 minutes. And again, this is 50% of our score. Now, we've got 2 questions, as you know, that are our biggies. Our biggies are going to be 12 points each. One of them is our experimental design, and one of them is our QQT. Now, let me talk about those 2 first. The experimental design, College Board's written it in a couple of different ways. One of the more obvious ways that they make it is they give you some sort of premise, and they say you design an experiment to be able to test for, let's say, velocity, or to be able to test for gravity, or to test for energy loss, okay? Any of those kinds of premises. And you come up with what materials you want to use, what those materials are going to measure, and the procedure that goes along with it. Now, let me say that again. You're going to pick your materials. You're going to say what those materials are going to be used for. So what are you going to measure using those things? Okay. What kinds of material are you going to get? What kind of data are you going to get from those? And then use that data. That's one general kind of experiment. A second kind of experimental question that they've been giving is, here's the experiment and here's some data that these students have come up with. Look at the data. Is the data reasonable? Is there an outlier? What would you do with it? A student came up with this equation versus this equation. Is that true? Is that viable, or is it not? Okay, so they've been doing experimental design where it's kind of all on you, where you create it. And they've done experimental design problems where they've kind of created it and asked you to truly analyze the experiment. Okay? Both ways are valid. Both ways they're going to have like A through, who knows, G, maybe some double I's and triple I's in there. But that's how College Board works. Okay? Now, on the experimental design, probably there's going to be a graph, or ask you how you would graph the data that you got, okay? How might you transform the graph if it came out as a curve? So these are those types of questions. Granted, since it's A through possibly G and some I's and double I's, it's going to take you longer. So hence, I'm asking you here to spend maybe about 25 minutes-ish, and that's your big points. You're going to go for every little point that you can. Okay? The second big pointer for us is going to be our QQT, qualitative, quantitative, and translating it. So here, you might be given a graph and an equation and a scenario and 2 students arguing. And you've got to translate all of that data back and forth and say what's valid. Again, you might have A through G again with some I's and double I's. and you're going to be interacting between those different parts. Okay, so again, this is a nice long one for us. Then we'll have a total of 3 short answers. 2 of those short answers could be an equation or working out a problem. If so, yay, maybe with numbers or maybe just an algebraic expression that we're deriving. Or it might be something where they're asking us about things that people have said or to evaluate some data. But the third one of our short answers, that's going to be our paragraph length response. And they always say in a clear, coherent paragraph length response, respond to this prompt. Now, on those paragraph length response, here's how I teach my students. Usually for the first point or two, they're asking you to look at the scenario and give your claim. So it's increasing, it's decreasing, it's working, it's not working, whatever the claim is, okay? Then you're going to spend the other 5 to 6 points explaining why that's true. Now, one of those points for those 5, 6 points is whether or not you're clear, whether or not you're going back on your own word, whether or not you're making it in a way that a person can follow you. So as long as your paragraph is kind of consistent and concise and you're using physics, most likely you're going to get that point. So try to make sure that you're in logical sense. Okay? That leaves us with 3, 4 other points in there. That's where we're making our argument. So think about 3, 4 different things about your scenario that you want to put down. And if you can kind of wrap your mind around that, most likely you're going to get enough information on the paper for the grader to give you those points. Now, a question I always get in the chat, and I haven't checked it yet, but I'm sure it's there, is, well, okay, I should start on those 2 biggies first and then go to the other ones. Not necessarily. It depends upon what the questions are asking, okay? If you just absolutely love energy and that's your thing, start on the one that has to do with energy, okay? Or if you just love rotational motion and torque, start on that one, okay? So whatever one really just turns your crank, start on that one. Knock it out, get as many points as you can, and move on to the next one. Ultimately, what you're looking at is getting as many points as possible from everything that's there, okay? So put an answer everywhere. Now, when you look at both sections of the exam, truly, you're not doing what we call a right there. You're not going to open a textbook and say, there's the answer, I should have memorized it. There's nothing on the AP exam here that's going to be right there in your textbook. All of the time, you're going to be using maths to solve problems. You're going to be looking at different models and diagrams to solve and figure out what's going on. You're going to analyze data. You're going to come up with experiments. You're going to judge other experiments, okay? You're formulating your own hypothesis. You're making connections. And this is on both sections. It's not just on the free response. There are also these types of questions within the multiple choice as well. So please realize this is a thinking exam. It's not a memorization exam. No 2 questions are identical year to year. They're always new. They're always fresh. So it's a matter of you thinking. So that's why I say, please don't stay up all night studying. Please have a good dinner, go to bed, have a good breakfast, and come into the test tomorrow morning being able to think and being able to process, because that's going to give you your best score. As long as you can process the material, you're going to rock it, okay? Now, a couple of little tidbits. That link that I put in the chat, that goes to here for our constants and conversions. Quite frankly, 99% of the time, you're not going to use it. You're going to use gravity, which is 9.8, and it probably will never leave your brain ever again. And you're going to use probably the universal gravitation from Newton. And that's about it. You may perhaps, doubtful, but you might have to use a metric prefix, but those are probably in your head as well. But the constant sheet is there just for you to have a touch base, make sure that you're good in case you need it. On the other hand, here's your equation sheet. And yes, you will use this. On our right-hand side, this part for the geometry and the trig, This is just in case I get really nervous in the middle of a test. And one year, everybody forgot the circumference of a circle. Like most of the US, they were so nervous. But if you do get stuck with something like that, look here because it's probably on the sheet on that right-hand side if you forget something silly like that. But most important is the left-hand side. Here's where all of our base equations are. Here's where our beautiful physics vocabulary is located. These are the words when you get to that paragraph length response. These are the words I want you to be using. These are the words that you're going to use when you're talking about physics terms as you're explaining or justifying your answer. This is where you go, okay? When you go to work out or derive an equation, you start here on any one of these equations. Start with somebody on the equation sheet and move from there. And you think, I know that, Ms. Ruiz. Of course you do. But here's the trick. If you start with one of these, that's probably worth 1 point on the multiple choice. And then as you're manipulating it and driving things, we're giving you more and more points on that free response. So start here and move from this location so that we can maximize all of our points there. Okay? All right. Let me go to the next one. Now, I know you know, but let's just talk through it for a moment. These are our concepts. So we've got kinematics, dynamics, circular and gravitation, energy, momentum, simple harmonic. Ooh, that looks like such a little part. Torque and rotational motion. All right. What's the biggest here, guys? Energy. Okay. Energy is not going to be asked most likely as its own entity. It's going to be sprinkled into everything. So if it's a free response question, most likely A, B, or C section is going to be something about energy, okay? And what do we typically do with energy? We usually have some sort of momentum going with it. So those two are oftentimes linked. As far as kinematics, usually if we have something with dynamics going on, there'll be some sort of kinematic thing where the object, we need to find the velocity, we need to find the acceleration. It can also be linked to circular motion. Maybe it's something like a roller coaster or something of that nature. Simple harmonic could be linked to anybody, okay? It's just a matter if it's a periodic motion and we look at where the force is maximum or the acceleration is maximum, okay? And torque and rotational motion, a lot of students say that last year's exam, it was all circular and all torque. It's not true. What we did is the exam questions had something about a circle in it, but it was a kinematics or a dynamics or a this or a that. So read the actual question, pay attention to what's there. Cool? Cool. So for our multiple choice, remember, they want you to think. It's not a rote memorization. It's specifically to see what's inside your head, and to see that physics knowledge. Sometimes the wording gets a little, verbose, okay, a little complicated. So it's okay to read the question twice. Or maybe you need to underline as you read it. Or maybe even you need to, read it more than 2 times. That's okay. No problem. It's more important that you know what they're asking and that it's very specific because they want specific answers. Okay? Anytime College Board spends money on diagrams or graphs or charts or anything of that nature, it costs them more than just typing out the question. So please look at every single diagram, look at every single graph, anything of that nature. Because it costs them more money, it directly relates to the question. So it's well worth looking and taking that extra couple of seconds. It usually helps to explain the text that's there and to give you a visual in your mind of what the person was trying to get at when they wrote that problem, okay? As you're reading the question, maybe you're an underliner. I'm a write it on the side and sketch on the side so I can keep track of what's going on. Whichever way works for you so that you know exactly what they want. Eliminate where possible. It's not always possible. but eliminate where possible. And once you're done and you put your answer, just double check the question right quick. Make sure you answered what they asked for. Did you read it too quickly? And they really wanted, let's say, tension, and you put down normal force, okay, or something else. You need to just do a quick reread, make sure you got what they wanted, okay? Pace yourself. On your multiple choice section, you should finish or be very, very close to finishing. So you've got a minute, maybe minute and a half per question. Some will come to you and you'll just, boom, know that answer in 20 seconds and move on. Okay, just go slow enough that you read it, okay? Others, you're going to get to certain questions, you're going to be like, oh, okay. That's the one that you kind of borrowed the time from the 20-second one, and you're going to spend your minute and a half, maybe 2 minutes there to answer that question. Okay, so if you don't know it all, remember, make a guess, make that consistent guess all the way throughout, pick your letter and stay with it, but do mark it on the side, because if you do have a couple minutes at the end, something might come to you. So you could go and fix that, okay? Please, please, please answer everything on the multiple choice, everything. In the olden days, won't tell you how old, but in the olden days, they used to penalize you for guessing. Not now. They will not penalize your guess. It's just wrong. So it's well worth you at least bubbling something, because who knows, you might have guessed correctly, okay? When you're truly stuck, go back to that beautiful equation sheet. I told you there's a lot there to help you. And practice, practice, practice. All these practice tests and questions you've been doing your whole year are going to come back and they're going to help. Okay? When you're on your free response, particularly read carefully. And if you'll notice my second bullet here of pre-read, that's what I was talking about before. So I get my free response, I've done my break, I've done my stretch, I've taken my deep breaths and eaten my snack. I've got to go through a whole nother 90 minutes of this test. Look at the test first. Okay, I like this one, I like that one. Ooh, I don't remember that part. Start on what you know. Nail that. Go to the next part you know. Nail that. And start working through the test. It could be that the one you like the best is the last question. Fine. Or it might be the first one or a middle one. It doesn't really matter. Ultimately, when we're grading it, we're looking at how many points you get overall, not necessarily how many points you get on question 4. So we're looking at that total. So it's well worth your time to kind of pre-read and say, oh, I like that one. That's where I'm going to begin. Okay. Write, please. Please, all of us graders would love for you to write perfectly, but write legibly. I know you're trying to be quick and you're trying to get your ideas down, but remember, we have to be able to read it. So make it as clear as you can. Let's say I start a problem and I start going down the wrong line. Okay, cross it off with an X and keep going next to it so we know where we're reading. Okay, so just show us where we're supposed to go. Organize what you're doing. If by chance, let's say you ran out of room, you could get extra paper if you needed. And from our perspective as a grader, we'll get that extra paper if we need to. So it's okay. Label what you're doing so we can follow you. And please, it's a generational thing. We were like this when we were your age. Please show all your work. I know your brains fire so quickly, but please pull somebody off the equation sheet, start there, show us how you're working the problem so we can give you as many partial credit points as possible. Usually we give a point for starting with the equation, and then if you have to substitute something in, there's probably a point in there. There's probably a point for manipulating it and getting it into the correct units or to the correct variables that College Board's asking for. So the more steps you're showing us, the more we can follow you and we can give you that partial credit. Okay. So every question, answer every part with something, even if it's just the equation. Every problem, every time. You're going to try to put something down in every single space. Okay. And just double check yourself right at the end. It's not frequent, but there are occasions where we'll give you a point for units. It's usually just 1 point and it's every, like, say 3 to 5 years. But more importantly than that is when we're deriving an equation, College Board says, I want it in these variables. So make sure your answer, your final answer is in those terms or those variables. Like, for example, if they said they want it as M naught or with the little 0, make sure you put your final answer with M naught. Or physical constants could be something like gravity or big G. Okay, so make sure your answer has those things in it. Okay, whew, we're getting there. So just a quick review for our units. So we've got kinematics all the way through rotation. So how I organize this is I put a quick little tidbit of what we should remember for each one of these units, and then I put in a couple of published multiple choice questions with their answers. So if I get tight on time, I will flip through them. So you will have this as a video that you can slow down and answer those questions directly. But I did put them in there, so we're reviewing each topic for just a quick little minute. Okay. Any questions you have, please put them in the chat. And I'm going to keep looking back and forth between the two screens to make sure I've got you. All right, our first one is kinematics. And when you started in the beginning of the year, you did position, velocity, acceleration, and you probably spent a lot of time here because this is when you first got kind of introduced to physics and physics terminology. Now, when you look back at it, you go, whoa, that was easy, okay? But at that time, it was a little bit difficult. And we do represent motion in different ways, don't we? We represent motion of where is that position? We do projectiles as well. So those were our big ideas that we started with. So here, let's start with this. Notice, oh my goodness, right off the bat, there's some graphs. So is that important? Yes. If they wasted the ink on it, it's important. And all these ones that I picked for you are published questions from College Board themselves that were given on past AP exams, okay? And I'm going to give you a little bit of time to read. Then I'm going to put the answer so that we can get through everything. So go ahead. I'll be quiet for a hot second. Okay, what are we looking at? We're looking at a position graph. We're looking at a velocity graph. We're looking at an acceleration graph. What's important about that spot right there? That's the spot where the velocity is 0. When the velocity is 0, aren't we usually turning around? We are. Notice the velocity starts in the negative and moves to the positive velocity. That should tell us something, okay? Usually we consider negative as going to the left on an XY plane and to the right is positive. Notice as well, the acceleration is above 0. Gravity, it's usually down here. Oof, pretend I can draw a straight line. All right. Think you got your answer? Hold on, I'm going to grab it. There you go. Does that make sense? You're rolling up a ramp and then back down. Okay, so we stopped for an instant and we came back. All right, try this. Now, 1 second. This particular one is going to be a set. Okay, so I'm going to have this graph, but I'm going to have it on more than one question. Now, notice it's a velocity time graph. College Board loves velocity time graphs. Why? Well, on a velocity time graph, the slope is acceleration. And the area under the curve is displacement. So you can get two things from a velocity time graph. So I'll hush and give you a moment. So we're looking for distance. Distance is kind of similar to displacement. Think through it. Think you got it? Where am I moving the greatest? From A to B, aren't I? Okay. Good. Okay. Now, notice, same premise. So this is our set. So notice the graph is the same. That first little blurb is the same with a cart is constrained, all the same, but totally different question, isn't it? Now, here, I want you to do something that's called ranking. Ranking means that I'm telling you like who's biggest, who's next biggest, who's the smallest. College Board has been going down this route recently. What do I mean? In the last few years, they've been putting more and more ranking tasks on the exam. They didn't used to do that so much, but nowadays, ever since 2014, it's become more of a consistent question. So think about this relative to acceleration. Now, acceleration was the area under, or was it the slope? Think about it. We got it? Excellent. Were you right? Okay. So this is not that bad. All right. But notice we're kind of having to interpret, aren't we? It's not just I opened up a book and this answer was right there. I have to know what that graph is. I have to know what to look for. I have to know what the words mean. All right, good. Kinematics, check. All right, quick one. Let's now go to dynamics. So in dynamics, we had to talk about what is a system. Now, here's one that kind of messes with students' brains. Now, if I have, let's say, an object and I move it to a certain height, okay, like for energy, but the Earth is not present. Okay, if the Earth is not present, I have put that object there. I have done work and energy to put it there. But if, on the other hand, Earth is present, don't we have a weight for that object because gravitation is pulling it down? So we started to talk about systems when we got here to dynamics. Do we have just the car or the car and the trailer that's moving? Okay, so you have to decide what system it is that you're looking at. We started to talk about gravitational field of things falling down due to gravity. What's the difference between contact forces and field forces? Contact forces are forces that actually touch. So something like a normal force or a frictional force or a tension. Something that's a field force, our biggest one's going to be gravity for us. But in other parts of physics, it would be like an electric field or the strong or weak nuclear. But for us, it's going to be gravity. Then you had the famous Newton's laws, 1, 2, and 3. And then the big time part of dynamics was us applying Newton's second law. So quickie, what is Newton's first law? Could you tell me? All right. Newton's first law is the law of inertia. I don't want to move unless you make me. Okay, so I'm going to stay at rest, or I'm going to keep on moving the way I'm moving at a constant velocity unless you push on me, you exert a force on me and make me change. I love to call it the teenage law. Teenagers don't move unless you move them. Okay. Third law and free body diagrams. Third law was, we typically said in physics classes, like an action-reaction pair. It's two objects interacting with each other. So if I had, let's say that I just had said a truck with a trailer, okay? The truck is interacting with the ground is interacting with the truck. So we have normal force and weight acting. But isn't the truck also acting with the trailer? And there's a pull between them as well. Okay, so you can start to see how different forces are interacting with each other. And then, of course, Newton's second law, our favorite, F equals ma. And then we start to put that together with various forces acting at one time. So here's an example. So all of these boxes are on ramps, okay? The box is given a sudden push up the ramp. Friction between the box and the ramp is not negligible. What does that mean? That means friction is present there. Which diagram best represents the directions of the actual forces acting on the box as it moves upward after the push? I'm going to hold for a second, see if you caught that in the reading of the question, because many people miss it. Okay. Did you notice right here, it says acting on the box as it moves upward after the push. So is the push still going on? No. So you cannot draw the push. Well, could we eliminate something? Well, if we're not doing the push, wouldn't that eliminate a couple of questions or a couple of answers there? Think of also, which way does friction move? Okay, so if the box is going up the ramp, friction should be opposing and going down the ramp. Were you right? Good. Notice also here in this diagram, did I do the components of the weight or just the weight itself? Here on the free body diagram, always just the weight itself, no components. When you need to work on components, you sketch it out on the side for yourself. Don't ever draw it on the free body diagram. Sketch it out on the side, so that's your notes, not on the free body. Okay, let's do the next one. Okay, this one would be a modified Atwood machine because we've got our pulley going back and forth and our tension on our cords. Okay. Now, for now, I've given you this with no inertia on that pulley. But when we add in unit 7, we could have that pulley have some friction, and that pulley has a certain distribution of weight, and so that pulley could have its inertia. Think like College Board does. They're going to add these different ideas together, most particularly on our free response questions. So let me give you a moment here. Now think, they're planning to measure the time the block A takes to reach the floor. The students must also do what else? So in other words, we're thinking here as an experiment. They're doing this. What else do they have to do? So you have to go back to your knowledge of being in the lab and what happens. What do you need to measure? Were you right? So again, it's not a right there question. It's something you have to come up with based on what's inside your head. Check on dynamics. Let's move on to circular. Now, circular is supposed to be a very small section, but there's a lot of information in there. Everything from what are the 4 fundamental forces of nature, gravitation, how does gravitational field work with the acceleration of gravity on different planets, what's inertial versus gravitational mass, centripetal acceleration, centripetal force, free body diagrams for uniform circular motion, and then applying this to planets and so on. So let's try one, okay? Another kind of question that College Board has been doing are these little boxes. Can you see them? So you have to say what's going on with the force, but here you also have to say what's going on with the speed. Okay, so 2 satellites are in circular orbits around the Earth. Satellite 1 has a mass of M1 or M naught and an orbital radius of 2 radius of the Earth, where RE is the radius of the Earth. Satellite 2 is a mass of 2m and an orbital radius of 3r. Which of the following correctly compares the force? Okay, where would we start here? Well, isn't the force Newton's universal law of gravitation? Sorry about my beautiful handwriting with a cursor. Over r squared, right? Okay, well, the gravitational constant, won't that be the same? We're going to put a 1. The object itself is going to be the same. But the mass of the first satellite was, where was it? Just mass. So we're going to call that just 1. And its radius was 2. So aren't we going to get about 1/4? Sound right? Okay. What about the second one? The gravitational constant is going to be 1. The item is going to be 1. What about the mass there? They say we are at 2 times the mass of the Earth. Okay. And in the denominator, our radius is going to be a 3 times that radius. Okay. So here, aren't we getting a 2 over a 9? That process that I just went through is factor change. You're putting down the change. So compare the two. Tell me what you think. Where you're right. So I've done the forces for you. How could you have done the speeds? What would I have done for that? Well, isn't the force for the gravitation, in a sense, equal to our centripetal? Because the force for gravitation is what's pulling us in. Couldn't we solve for this velocity in a similar manner to be able to get it? You see how we're using things to get to our final answer? Now, this one would have taken me longer. This one would not be a 30-second, 20-second. This one would take me a good minute to do to figure it out. All right, here, we've got a diagram. Again, notice, what do we have here? I'm giving a diagram and a premise. So here's my diagram, here's my premise. I'm doing this premise on circular motion and gravitation, then I'm going to move it to energy. So this same premise. So think about it. Which of these is true of the net force on the block when it's here at position C? So it's going around the circle. So what's the force going to be at this location in the circle? Think it through. Got it? Were you right? So they're going to have forces going down for the weight, but isn't the centripetal going inward towards the center of the circle? Excellent. So again, we're going to use that premise in a hot second. Let's go to energy next. So with energy, we have to talk about open systems and closed systems. Closed systems are isolated. Nobody's acting on me. Okay, just what's in the system is acting. Open systems, I can have an extra push. I can have some extra work or energy added. I could have extra work or energy subtracted. Maybe I have friction. Oh, that might change what's going on. Okay, so you have to think about, is it an open system or a closed system? We're going to talk about work and mechanical energy and all the different energies of kinetic and potential gravitation and potential elastic. And we have to think about that conservation of energy, how energy is not created or destroyed, it's just changing forms. And our work kinetic energy principle or theorem, depending on your teacher, and of course, power. So remember, I promised that premise. Here's our premise again. Same diagram, same premise, but now we're looking at this same scenario, but through energy instead of circular. So after the block is released from up there at A, which of the following sequences of position is the speed of the block ordered from fastest to slowest? Aren't we ranking it again? We're ranking it from fastest to slowest. So here we're using energy instead. Let me give you a moment. Were you right? Okay, excellent. Well, let me go back for 1 second. Why at B? Why is it biggest at B? Well, isn't that going to be the location where we've gone from potential energy gravitation to all kinetic? Okay, so we've had that exchange, haven't we? All right. Let's try this one. And you've probably done this one in your lab, where we released objects from rest at the top of a ramp and we let them go down. Now, what's slipping and not slipping? Slipping means the object's actually going to slide down the surface. So kind of like ice. Okay? If there's friction, though, the object will roll. Okay, so with the ball there, if there's no friction and it slides, it's going to slide in the kind of same manner as the block. But if friction is present, that ball will roll as it moves. Okay, so that's your distinction. Yes or no with the friction. If friction is present, it's not going to slip. Good? Okay, so let me let you think here. The block slides down the ramp without friction. The sphere rolls down the ramp without slipping. Which object will reach the bottom of the ramp first? So think of energy, but you might also be thinking of rotation a little bit. Think you got it? Okay. Why? If the ball is rolling, okay, and they say the sphere is rolling, we're going to have kinetic energy translationally linear, and we're going to have rotationally, okay? So we're going to have both of those acting, not just the translational. Hence, the block will hit it because it's not going to gain that kinetic energy that's rotational. The sphere will. Okay, check on that one. And I did kind of combine a little bit of rotation there. Let's do momentum. So there's momentum and impulse. What's the difference? Remember, impulse is the change of momentum, okay? So it's what momentum changes over time. We're going to have different kinds of representations of that change of momentum. We have the FT, the force times time, but we also have the change of momentum as mass velocity final minus mass velocity initial. Again, we're thinking of those open closed systems. Can I add something? Can I subtract something? Or is it just that system itself? And we do have our second, our second in physics conservation law, conservation of linear momentum. Let's try a couple of those. Here's a beautiful cart. And since you've seen my drawing ability, I did not draw that. Okay. It's an open cart on a level surface and it's rolling without frictional loss, okay, through a vertical downpour of rain. Okay. The rain is coming in. Would that system be closed or would that be open? Wouldn't it be open because the rain's being added? Okay. As the cart rolls, an appreciable amount of rainwater is accumulating in the cart. What will happen to the speed? So this is kind of open. The friction's not happening on the wheels, but we do have all of this extra mass being added. So it is open. What do you think is going to happen? Were you right? Okay. Is it going to be able to go as fast? No, because we've added so much more mass, that cart's going to slow down a bit. How about here? Now, I don't know if your teacher showed you a graph like this. So let me just look at the graph first before we answer the question. Notice we've got block 1 up here and block 2 down here, but then they come together and it's block 1 and 2. So that infers to me that block 1 and 2 are stuck together. What does that tell you? If I'm stuck together, am I elastic or am I inelastic? Which one am I? I'm inelastic, aren't I? I'm stuck. So what do we know, even before we read it? If I'm inelastic, momentum is conserved, but kinetic energy is not. Okay, why is kinetic energy not conserved? We've lost it due to deformation or breaking of the object. We've lost it due to some energy due to sound. We've lost it maybe perhaps due to some heat energy. Okay, so that particular graph is very diagnostic. I don't know if your teacher showed you one or not, but you could read that already from the graph before you even read the question. That's why I'm saying their graphs and their pictures and their diagrams are so vital, because it tells you so much information before you even start. Let me give you a moment. Got it? Were you right? Again, use the graphics to help you. All right, check mark on that one too. Let's hit simple harmonic, our very smallest unit, but it is applied through various questions. What we're really looking for here are two scenarios. Our simple harmonic motion as far as the period of a pendulum, the period of a mass on a spring, and then also the energy that's there for either one of those. Okay, and to trace out their motion to see how it's moving back and forth. Here's a particular example. Notice again the boxes we're comparing. Okay, we're looking at object's mass and string length for a pendulum. So since it's object mass and string length, don't we need to know the period of a pendulum? And we just copy it straight off our equation sheet. Okay. So it has a simple mass at the bottom, string length is L, period is T. Which of the following combinations of mass and string We'll also have a period T. Okay, so what do you think? Look at the equation. Do I see mass in there at all? No, I really don't. So is mass going to really affect the period of a pendulum? No. However, if we put the period of a mass on a spring, would we have mass having an effect? Definitely. Okay. Would we have the length of the spring having an effect? No. So again, use that equation sheet when you're nervous. It helps a lot. Were you right? Excellent. All right. Oops, I forgot to erase. Sorry about that. There we go. Okay. Again, notice here, graphs on top of graphs with more graphs. Oh my goodness. Okay. This one's an expensive one for College Board. They had to make 6 different pictures for this one question. So here, we've got a potential energy graph on the top as a function of displacement, okay, on a spring going back and forth with simple harmonic motion. Which corresponding graph is the kinetic energy one? How do kinetic energy and potential energy go together? Doesn't it go from potential to kinetic and kinetic back to potential? And this is potential energy on a spring or an elastic medium instead of gravitation. Wait a minute. When I'm a spring, isn't the potential energy, sorry, trying to write, is 1/2 kx squared, right? And if we're doing kinetic energy, aren't we 1/2 mv squared? So both of them have squares in them. What does that square part tell you? Should it be a line or should it be a curve? What is that telling you? Think you got it now? Were you right? Excellent. All right, let's get to our last section of rotation. Now, technically, it's a tiny section. Technically, you're looking at rotational kinematics. So you're taking all the kinematics from Unit 1 and putting them in a circle. You're taking torque and angular acceleration. So you're taking F equals ma and putting it into rotational context. And then also adding the inertia and the acceleration. Then you get to momentum. Again, going from linear to angular, and then conservation. So for example, what I mean is if we think of force is equal to what? M times A, right? Couldn't we do torque is equal to I times alpha? We've gone from linear to angular. What about momentum? We have momentum is mass times velocity. So haven't we done angular momentum is now I times omega? Okay, we've gone from linear to angular. There's so many things here in this particular section that everything has gone from linear to angular. So that's really a beautiful crutch to help you as you start through this section. Let me do the kinetic energy too, because that's a very familiar one. 1/2 mv squared. And that now changes into 1/2, what do you think? I omega squared. We've just moved it in to its angular form. So that's kind of beautiful. Now, let's try this one. Okay, we've got a diagram, and notice they're telling us we're looking at it from above. So we're looking down at it. Sometimes they tell you you're looking from the side, but here they're specifically saying you're looking down on it. A kid of mass m is on this platform or merry-go-round, and the merry-go-round's like 2m, and it's going counterclockwise. Remember, counterclockwise is like a unit circle. That's going to be positive. Clockwise is going to be negative. We always kind of are like math, so we're going to go with the unit circle as positive. Assuming the platform rotates without friction, which of the following describes an action that the child could do that would increase the speed? So it's going to increase how fast this thing is rotating. Think about it. What's going to help me go faster? Were you right? Okay. Think about an ice skater. Don't they pull in their arms and they go faster and faster and when they spin? Okay. The real world, it's physics. You gotta love it. All right. Oh, this is the first one I've seen like that. Look, the answers aren't circles, they're squares. What is that telling me? That's telling me to pay attention. This is one of those ones when you're selecting two answers. This would be like one of those last 5 questions on your multiple choice, where you've got to pick 2 things correctly. Okay. So again, what if I pick one of them wrong? Do I get double counted wrong? Do I get half credit? No. This counts the same as any of the other multiple choice I've done through the whole time. Okay, so this counts exactly the same. So go ahead and think it through. 2 answers, remember. Were you right? Okay. Since this takes a little bit more work, you may want to leave these last 5 till the end. Or if this is particularly easy for you, start with these 5, okay? It doesn't matter. You pick the ones that work for you. And again, if there's an answer that you just have no idea, please on the multiple choice, put something and keep that something consistent, okay? So we've hit all of our units quickly right before the test. So again, tremendous good luck to all of you. The biggest thing I can suggest to you is to please don't spend all night studying. Please go to bed so that you can be fresh in the morning and you can think physics. If you've noticed from every single question I've given you here today, all of them are not right there kinds of questions. You have to apply and think of your physics knowledge and what does that mean, and then use that to answer the questions, okay? So you're using your knowledge. It's not something that just you regurgitate right on the paper. Think it through. You know a lot in your head. Apply what you know. Make sure on your free response, start with one of the equations from the equation sheet. Show us all that work so that we can see what you're doing so we can give you that partial credit. One other thing, say they have you do a graph. Please don't be a student who's saving paper. They give you a whole piece of graph paper. Please use 3/4 of it. When you're using most of the piece of graph paper, that's when we can see a trend that's a line maybe, or maybe it turns out as a curve. And so when it's turning out as a curve, we'll see that on a nice big graph, but we won't see that on a little bitty tiny one where you're using 2 or 3 boxes. So use the graph appropriately. When, say, you're graphing, what if it comes out as a line, okay? But your dots are not right on the line. Remember, as best as you can, best fit line. Equal numbers above, equal numbers below. Draw your best fit line. Do your slope based on your line, not on your data. Do it based on your line. Good? Good. All right, you guys can do this. Remember, good sleep, good breakfast, use those brain cells that you've been working so hard this year. Use that equation sheet and you're going to rock this test. Steal every little point from every little spot that you can so that the overall total is going to give you that 5, okay? And for all of us here at Marco Learning, remember, keep us in mind. Come say hi on our website, social media, tag us as much as you can. And we're here for you guys. So whenever you need us, please come see us. All right? All right. You guys have a good one. All right. You can do this, guys. You can do this. Any extra questions?